Hi, everybody, and welcome to the very first IRINA seminar of this 2024. So I'm Denise Piatti, and I'm a researcher at the University of Padova, and today in Italy. And today I'm very happy to host a colleague of mine, Federico Ferraro, who is a researcher at Laboratori Nazionali of Gran Sasso, one of the largest active underground laboratory. And Federico is a colleague of mine since he is a collaborator of LUNA experiment. LUNA stands for Laboratory for Underground Nuclear Astrophysics. And today he's going to give us some updates on the activity at present activity and future activity at LUNA. So for those of you that just joined the meeting, Federico said that he prefers to be interrupted if you have questions. So if you have questions, please go ahead. And okay, so I think now it's time to leave the stage to Federico. So please, Federico.
Okay, anyway, if you feel uncomfortable in interrupting, you can also ask in the end, no problem for me. So let's start with it. I'm going to talk about this present and future of nuclear astrophysics at LNGS. And this means that I would like to give you an overview of what is happening now and what happened in the past at LNGS, especially in the context of the LUNA experiment. So first thing that I would like to go through is some words about nuclear astrophysics and what it actually is. So coming to this topic, nuclear cross-sections are the most relevant player in this field. And as you can see here on these slides, nuclear cross-sections are relevant to different fields, different topics in physics, starting from stellar evolution, but it includes also nucleosynthesis, astronomy, so the evolution of the solar system, but also stellar neutrinos and the evolution of the early universe, because all of these fields are very deeply connected to nuclear reactions and actually their cross-sections and the probability that they happen in the specific environment that we are looking into. So what can we ask when we are going to study nuclear reactions? What can we look into? And what is the most important thing that we have to consider? Well, actually, in such an environment where nuclear reactions take place in these astrophysical scenarios that I talked about a little before, what actually is so important are two things. So basically, we have the interacting nuclei, and here, if we consider a reaction A plus B that go into C plus D, we have to consider the interacting species. So the effective number density of element A and element B, so the interacting species, and their velocity, because the distribution of the energy of this interacting species follow a Maxwell-Boltzmann distribution. So all of these nuclei inside the plasma have different energies, and these energies are distributed as a Maxwell-Boltzmann distribution. And then there is another player in the game, which is the cross-section and the tunneling probability through the Coulomb barrier. So when we consider all of these into account, we end up with a reaction rate that is basically given by these players. So the density of the interacting species, and in this integral here, we have the Maxwell-Boltzmann distribution as a function of the velocity and the cross-section of a function of as a function of the velocity. And their multiplication here in this integral corresponds to this peak that you see here on the right, which we call the Gamow peak. And this Gamow peak defines the most important energy interval where such reactions take place. So the actual energy range that we are interested in studying. But let's go a little forward. And we just have to consider that usually this Gamow peak, this gamma window, happens to be placed at very low energy. And at very low energy, there is an inconvenient behavior of the cross-section because it falls down very quickly. And as you can see, well, the situation can get very bad very soon. So introducing some factorization of the cross-section, we can factorize the Coulomb interaction term apart, as you can see here. And the Coulomb interaction term is this green term here. And what is left is what we call the astrophysical factor, S. And as you can see in the plot here on the right, the astrophysical factor has a way smoother behavior as a function of energy, and it does not drop so abruptly at low energies. So what we can think about is to extrapolate the behavior of the astrophysical factor at energies which are lower than the lowest energy that we can look into. So we can measure down to the lowest possible energy and then extrapolate just below. But this is not something very straightforward because something unexpected may happen and spoil our measurements, our knowledge of the cross section eventually. So unexpected low energy resonances may be there. So there could be a misestimation of the cross section, which is very different from what we believe if we just extrapolate down to unexplored direct energies. But let's look into some numbers here. So considering that the counting rate is given by the beam flux times target nuclei areal density times the cross section times the detection efficiency, well, all of these quantities are quite small in this field, in nuclear astrophysics, in direct measurements. So we have a beam flux which is about 10 to the 14 particles per second, which means a current of sort of 100 microamps. And the areal density of target nuclei is not that big because it's just 10 to the 19 atoms over square centimeter. The cross section, you know, is very small. And well, the detection efficiency, I indicated 0.1%, but it could be even smaller. I mean, with these numbers here, we end up with a few counts per day. And these may be a very low counting rate, especially if we compare it to the background that we may have in a surface laboratory. And for this reason, it's fundamental to suppress the background quite strongly, and this can be obtained by going to underground laboratories. So, which is the situation of the underground laboratories all around the world? Well, we have basically these four. And as you can see, in the US, there is CASPAR, and it is 4,300 meters water equivalent deep. This CASPAR has an accelerator with a terminal voltage up to 1 megavolt and is able to accelerate protons and helium ions with a current which is going up to 250 microamps. And this is operating since 2017. When you look at the other side of the world, we have JINA in China, which is 6,700 meters of water equivalent deep, and it has this 0.4 megavolts accelerator, which is able to provide also helium-2 plus beams with very high currents, though, and this is operative since 2021. Then if we go back to Europe, where I am now, well, there is the Felsenkeller laboratory in Germany, which is 110 meters of water equivalent deep. It has one accelerator, which is able to provide a terminal voltage up to 5 megavolts. And it can also accelerate carbon ions up to a current of about 30 electrical microamps. But in the place where I work, we have two very powerful and very nice accelerators. One is the Luna accelerator, and the other one is the Luna MV accelerator in the Bellottia in-beam facility. And these two machines are 3,400 meters of water equivalent deep. The first one is 400 kilovolts in terminal voltage, and it can accelerate the proton and helium beams, while the second one in the Bellottia facility is 3.5 megavolts in terminal voltage, and it can also accelerate carbon ions. The current the both are able to provide is quite high, and while the Luna 400 kilovolt accelerator is operative since 91, the 3.5 megavolts is operative since last year. And both are inside the Gran Sasso National Laboratory here in central Italy. And the laboratory is situated under 1,400 meters of rock under the Gran Sasso Massif. And this rock overburden provides a muon flux reduction, which is about a factor 10 to the sixth. So a million times, a million-fold reduction in the muon flux, and a neutron flux reduction of about 1,000. So this is an effective shielding against the cosmic ray-induced background inside our detectors. Luna 400 accelerator is located here in this place, while the Luna megavolt in the Bellottia facility is located in OB in this very big hole that is in the middle of the underground lab. Now, what do I mean with background reduction? Well, you can see this, what I mean here in this plot, because you can see that, well, the green spectrum has been acquired on the surface. And as you can see below the 2.6 MeV threshold here, well, we have basically radioactivity, natural radioactivity, while above 2.6 MeVs, well, we have mostly the background induced by muons. So as you can see, going from the surface lab, green plot, to underground lab, the red and the blue plots, well, everything changes quite a lot. But what changes the most and what we are most interested in is the reduction in the background above 2.6 MeV. So if you look in this high energy region here, well, the gamma background induced by cosmic rays in the surface is not anymore present underground because it's reduced by a factor 10 to the 4. But this does not only apply to gamma spectra, because if you look at neutrons and charged particles spectra, the situation is quite good too, going underground. So if you look at the neutron spectra, well, the surface spectrum is the black one, while if you go underground, you see that the background is very much reduced also for neutrons. So you can also be able to see the differences due to the different material that you're using to build the helium-3 counters that it's used for acquiring this data here. And when you look to charged particles, well, the situation is improving by going underground also for charged particles, not at the highest energies here, but especially in this area in between 1 MeV and 3 MeV. Now, the Luna collaboration has quite a lot of expertise that acquired over the past 30 years. This collaboration is formed by members from these 4 countries here, so Italy, Great Britain, Hungary, and Germany. And here you can see the people that are collaborating inside the Luna collaboration. And, well, Luna has been the only underground accelerator for nuclear astrophysics for 25 years and counting, actually. And, well, its results are pretty good in different fields, including solar physics. And with this, I also mean solar neutrinos. I will show you later something about this. And the cosmological model, Big Bang nucleosynthesis, and stellar nucleosynthesis. And I will show you this in a while. But I would like to show something like from an history book right now. So we have these pictures. The one on the left, well, it depicts the Luna 50 kilovolt, which has been working in the Gran Sasso lab between 1991 and 2001, and then it has been decommissioned. And in 2001 arrived the Luna 400 kilovolt accelerator that you can see in the upper right corner here. And this includes a bigger accelerator and two beamlines, as you will see later. But since last year, well, we have this Luna megavolt accelerator, which is this big guy sitting here. And it also has two beamlines, and it's already operating since last year, basically summer last year. And will operate hopefully for the years to come. But let's start with something from the past, this Luna 50 kilovolts. Well, this was an accelerator that was able to provide hydrogen and helium beams up to a voltage of 50 kilovolts. So, I mean, it was quite low energy. The beam currents, though, were quite good, up to 500 microamps, and the energy spread and stability were exceptionally low. So very good performances for this guy. And this actually allowed this one historical measurement about the helium-3, 2 protons, helium-4 reaction that was actually something that solved ruled out the possible nuclear explanation to the solar neutrino problem. So if you look at this plot, well, you would realize that the points that Luna measured are sitting just in the middle of the gamma peak for this reaction to take place in the sun. And these are the only points that could solve the solar neutrino problem, because at that time it was supposed that the resonance inside this energy interval could effectively explain the missing neutrino that were not observed at that time. Ruling out this resonance was what allowed to rule out also the nuclear explanation to the solar neutrino problem. Then I would like to spend a few words about the Luna 400 kilovolts that is still working today. A little bit old maybe, but gold actually. So this machine is providing proton and helium beams, and we can accelerate them with a terminal voltage up to 400 kilovolts. And the beam current is very high. It goes up to 1 milliamp in the very best occasions. And the energy spread and stability are wonderful again, because they are making us able to perform very long measurements without any significant change in the beam energy and without any significant change in the beam current as well. So this machine is provided with two beam lines, as you can see. The first beam line here on the top, well, this is quite an old picture. So you can see here that we had a windowless gas target with 3 differential pumping stages. And this was also provided with gas recirculation and purification system. Here you can see quite a massive lead shielding with some germanium detectors sticking inside. But here you can see also a second beamline, which is for solid targets. And this beamline is provided with liquid nitrogen cooling for the cold trap and has the capability to wobble the beam on target so that it never damages too much. This accelerator actually provided us some very good results. Actually, we were able to measure the cross-section of the deep gamma helium-3 reaction, which is extremely important in different fields. So actually in 2002, well, we measured this reaction in this energy interval here, down here. So this was relevant for the proton-proton chain in the sun. But recently we measured this reaction in another energy interval from 70 basically up to 390 something kilo electron volts. And as you can see, we have a data set here which provided us with this wonderful result. And with this measurement, we were able to address the most uncertain nuclear physics input to the BBN calculations, and our measurement was actually able to improve the reliability in the use of these primordial abundances as probes of the physics of the early universe. And this allowed us to actually obtain the baryon density, and I mean, this is quite an interesting result just by comparing the relative deuterium abundance with respect to the expected abundance, and assuming a certain number of effective neutrino species, we were able to obtain the baryon density, which, as you can see, is very similar to what Planck measured, but now we obtained this baryon density with a complete different methods and with complete different systematics. And it's very wonderful how these two measurements agree. But these days, and I mean today, the situation looked very different at the Luna 400 and the 400 kilovolt accelerator, because the setup really changed a lot recently, as you can see here. And we have this new beamline, which we installed recently for other studies that we intend to perform in the very next future. And these two reactions are what we are going to study. And the setup for these two reactions are actually in commissioning and in these days. So let's start with the sodium-23p alpha reaction, which is studied in the context of the ELDAR ERC project, which stands for Elements in the Lives and Deaths of Stars. So this reaction is part of the neon sodium and the magnesium aluminum cycles, which are active at temperatures of about 0.05 gigakelvin. And well, this reaction might explain the anti-correlation between oxygen and sodium in globular clusters. And quoting Renzini, well, this discrepancy would be much alleviated if the cross-section of the sodium-destroying reaction were actually a factor of a few lower than the current estimate. So we are going to study the cross-section of this reaction just because we would like to understand whether this explains actually the anti-correlation that is observed in these clusters. And the uncertainties on this reaction is already, I mean, is still too high to answer such a question that Renzini posed some years ago, but we intend to address it. And we would like to use a setup which is derived from a previous version of the setup that you can see here. So on the left, you can see that the target chamber that we previously used is quite a dome. Let's call it dome. So the beam arrives from the direction indicated by this red arrow and impinges on the target, and the alpha particles scattered around while they are detected by the silicon detectors that are placed around. Well, we thought about an upgrade, and we ended up with this new guy here, the new target chamber, which includes, well, some copper pipe for the cooling of the preamplifiers, but it includes for sure these Hamamatsu pin diodes that are responsible for detecting the charged particles coming out of this reaction. So let's go on and talk a little about the next reaction. So the nitrogen 14p gamma, oxygen 15, and this is part of the social project, which is a project financed by the ministry, the University and Research Ministry here in Italy. Social stands for Solar Composition Investigated at Luna. And this is part of a wider effort that we are spending on nitrogen 14p gamma, oxygen 15. That includes also measurements at the new accelerator in the Bellotti facility. So let's go a little deeper into it. This reaction is actually the bottleneck of the CNO cycle because it's the slowest one at these temperatures at least, and this means that it controls the speed at which the CNO cycle takes place, and therefore, well, the number of neutrinos, so the neutrino flux that we can expect from the sun. And as you can see here in the right, at the temperature of the sun, we expect the CNO cycle to be subdominant, but going higher in temperature, meaning going to higher mass stars, while the CNO cycles becomes more and more important and overtakes the PP chains as energy generation rate and becomes more important. So looking at these plots, we can understand that for a given core temperature and with different reaction rates and metallicities, we can expect the energy production from the CNO cycle and the PP chain to be equal for different masses of stars. And on the right here, you can see what this means looking at the Hertzsprung-Russell diagram. And it basically means that when the stars with different masses are going away from main sequence, they are going away in a different way. So they are departing in different ways from the main sequence as soon as they start this deviation from it. So again, about this reaction, we intend to study it both at the 400 kilovolt accelerator and the 3.5 megavolts. I'm here talking about what we intend to do at the 400 kilovolt accelerator. Well, we have to study this reaction over quite a wide energy range, and we would like to address all of the transitions inside this reaction with 5% precision. And we believe that we would be able in this way to provide a definitive solution to the solar metallicity problem, provided that neutrino experiments are reaching the sensitivities that they need to provide good data as well. So the goal of the social project is to measure this cross-section below 100 kV, to measure the total cross-section in that very low energy part of the spectrum, and then to measure this cross-section in between 100 and 370 kV, to measure the contribution of different excited states to this cross-section and the possible transitions, and distinguish them very efficiently. And what we will intend to use to distinguish this different excited state is to use a segmented high-efficiency detector, which is basically what you can see here. So here we have a BGO detector, which is segmented in 6 parts. So we have this detector, which is actually some 30 centimeters long, and having these 6 segments, well, we can see both the sum peak, summing all of the energies inside all of these segments, and we can just look into each segment and distinguish the different photons that gave signal inside them. So it is possible to determine the cross-section more precisely, mitigating the summing in problems, which caused some problems, say, in the past, and in the determination of the cross-section of this reaction. But now, I would like to introduce the new accelerator, the new Luna megavolt accelerator, which is part of the Bellotti ion beam facility of the Laboratori Nazionali del Gran Sasso. This accelerator is an inline Cockcroft-Walton accelerator, which means that we have this terminal voltage, which is generated by this very stable generator, and allows to reach terminal voltages up to 3.5 megavolts. And this this will allow us to go in a different energy region that will allow us to study helium burning reactions, so and carbon burning reactions. So we will move into a different era of stellar evolution with this new guy here. And the beam energy reproducibility and stability are wonderful, so that we will be able to address these measurements with very high precision and accuracy. And the stability is very good, so that even longer measurements will be feasible. This accelerator can provide beams of protons, helium, and carbon ions. And as you can see, the currents are quite high. So we are talking about 1 milliamp for protons, 0.5 milliamps for helium beams, and 100 or 50 particle microamps for carbon ions, which is remarkably good. Now, what do we intend to do with this machine, with this fantastic machine? Well, we proposed to the Program Advisory Committee to carry on 3 different studies, 3 different experiments. And the 3 of them are listed here. The nitrogen-14 P gamma is the first one, and this has been approved and already started. And this is perfect as commissioning measurement because we already know quite well the targets. We already quite know how we can measure this reaction. And it has, for sure, an interesting science case that we would like to address. Then the second one is the neon-22 alpha N reaction, and this also has been approved and started, and this is part of the SHADES ERC project, which is a scintillator helium-3 array for deep underground experiments on the S process. And the last one, the carbon-12 plus carbon-12 process, well, this is waiting for approval, but despite this waiting, we are already keep going, and we are doing a lot of work to be prepared for this summer, actually. And this is part of CABS project, which stands for Carbon Burning in Stars, financed by the Research and University Ministry in Italy. And now, again, as I told you, this nitrogen-14 P gamma reaction, we would like to investigate the non-resonant component at the new accelerator, and especially we would like to address the weak transitions to the ground state, and we will take particularly care of the summing in corrections and the angular distribution effects so that we can measure accurately this cross-section all in a wide energy range. So this is the experimental setup that we are using, and it includes, of course, the accelerator, but it also includes 3 high-purity germanium detectors with very high energy resolution. And as you can see, they are mounted on guides so that they can slide and go closer or farther away from the target that sits here in this position. So we will study in this way the summing in effect, and we can minimize it, and moving the detectors as well on top of this table. As you can see, they are also able to rotate. We can also study angular distribution effects. And this is how the setup actually looks like. This is a picture that I took today. So here you see the accelerator. The beam is going out of the accelerator, coming into this tube. Here is the magnet that basically decides where the beam should go, into this beamline or the other. Well, we would like the beam to go into this beamline for this reaction, and the beam reaches the target that is sitting here. And you see these tubes. These are for the cooling water that we use to cool down the target itself while the beam heats it up. And all around you see, well, this detector here, this germanium detector, which always stands at 90 degrees with respect to the beam direction, and these other 2 guys that are able to change the angle with respect to the beam axis, and to also change the distance from the target so that we can study the summing in and angular distribution effects. But now let's go to the second reaction that I would like to talk to you about concerning this new accelerator. And this is the neutron 22 alpha N reaction, which is a neutron source for the weak S process. So let's talk about this before going into the details. Well, the weak S process takes place during the thermal pulses in quite massive stars. We are talking about stars that have a mass higher than 8 solar masses. And well, during the thermal pulses, this neon 22 alpha N, which is ignited right below the hydrogen burning shell, is actually providing a lot of neutrons for the slow S process, for the slow neutron capture process, so that a lot of new elements can be generated, and they are generated going up in this chart, and we can actually reach from iron to yttrium and explain in this way half of the elements in between iron and yttrium. But what is the situation of the literature? What is the status of the art for this reaction? Well, the cross-section is now quite uncertain, and with quite uncertain, I mean actually very uncertain, because practically there exists no data in the gamma window for this reaction. Well, actually, this is not completely true, because we have this resonance here, which is sitting inside the gamma window, but this is something like in a very small energy range. And if you look elsewhere, all around, well, we only have upper limits here. We cannot see anything really useful for determining this cross-section quite well. And the reason for that is that the counting rate for this reaction is very low. We're talking about a few reactions per minute. And, well, the upper limits that we have span a very large energy interval, which is approximately 300 kilo electron volts wide. Moreover, many states can contribute to the cross-section, so the situation is even more unclear. And as you can see in this plot, well, we intend to reach quite a low sensitivity, quite a great sensitivity actually, to investigate the lowest reaction yield possible and go as low in energy as possible in the measurement of this cross-section. Now let's talk a little bit about the background for this reaction. As you can see, this particular reaction has a negative Q value, which means it's endothermic, so it's even more difficult to actually study. And if we look at different reactions that might be dangerous for this measurement, well, we can see that we have boron 10 alpha N, boron 11 alpha N, and carbon 13 alpha N, and all of those reactions have a reaction cross-section that is higher compared to what we would like to measure. So it's extremely important to us to minimize the beam-induced background. And this means that we have to use enriched neon 22 and have a very good sensitivity and use low background detectors. And this means that actually we did good in trying and provide a setup which is able to measure this reaction. And this is what this setup looks like. It includes helium-3 tubes plus liquid scintillators. And as you can see in this image here, the helium-3 tubes are in this purple color, while the scintillator is inside these cylinders with this green cap. So all of these pieces are included in a matrix of polyethylene so that neutrons can also be moderated a bit. And this is to both maximize the efficiency, still providing some capabilities of particle discrimination because of the properties of the liquid scintillator that we are going to use. And here, this picture is maybe not very good in quality, but you can see Andreas here working at the gas target, which is inside this tube here. So basically the beam comes out of the accelerator, goes to the magnet, goes into the second beam line here. So not the one that we use for the nitrogen 14, the other one, and goes all the way to the gas target here. And then after the target finishes, it goes on onto the beam stop, which sits here. Then the last reaction that I would like to talk to you about is the carbon 12 plus carbon 12, which is actually the trigger of carbon burning in stars. And this is to explain a bit why this reaction is so important to us. Well, its cross-section it's strictly related to this parameter, which we call m up. And depending on this parameter, well, we can say something about the evolution of the star. So if the mass of the star is greater than m up, we can expect it to go through quiescent carbon burning and end up its life as an oxygen neon white dwarf, or a core collapse supernova, neutron star, or maybe a black hole. But if the mass of this star that we are studying is lower than m up, we can expect this star to never need carbon burning. And this will mean that it will end up in a carbon-oxygen white dwarf, in a nova, or in a supernova of type 1a. And if you look at this plot here, you can see what would be the effect of a larger cross-section due to the presence of resonance at 1.5 MeV in this cross-section. So if this resonance exists there, well, this ratio m up, so basically the value of m up in units of solar masses, would go down, would lower by 2 solar masses. So a lot of stars would actually go from one category to the other. And this means that we could expect a larger number of supernovae of type 1a, or a smaller number, depending on what the cross-section is like. Now, what is the situation for our knowledge on this reaction? Well, the situation is pretty bad because several data sets and models exist, and direct measurements above 2.1 megaelectron volts are affected by very large scattering and uncertainties that are very large. But we have some indirect measurements below 2.1 MeV. The problem is that sometimes it's not trivial to understand the normalization of this data. And as you can see here, we have different trends for this indirect data and different normalizations as well. So the situation is not trivial at all. And this is the reason why we have to measure this cross-section directly right in the Gamow window. So what would we like to do? What do we intend to proceed? Well, we would like to measure this cross-section down to the lowest possible energy. And this might be possible looking not at the particles, but at the gammas coming out of this reaction. So considering that about the 50% of the reactions in between these two carbon ions leave the final nucleus in an excited state, well, we can look at the photons emitted in the de-excitation of the nucleus in this excited state. And this de-excitation very often involves the transition from the first excited state to the ground state of the final nucleus. That means that for the alpha channel, we can expect this photon here at 1634 keV to be highly populated, and this transition at 440 keV to be highly populated in the proton channel. But nevertheless, we will also be able to see all of the other gammas in these transitions so that we can also tag better the reactions that we will observe. Now, the experimental setup for this study includes this very massive shielding, which is made of lead, And as you can see, it is on top of this very strong table. Very strong because this lead shielding weighs 12 metric tons. And inside this shielding, we will put a germanium detector, which I'm not sure you can see very well, but it's inside here in the very middle. And this will be the very first setup that we intend to use. And then to go to the lowest possible energies, we will also include a sodium iodide active anti-compton veto around both the germanium detector and the target that will sit here. So the beam comes in this direction. In this picture, the beam line is not included, but the beam will go just right here where it will meet the target. And the germanium detector will sit right behind to have the maximum possible efficiency in detecting those gamma rays. And here, basically, you see a sketch of the setup. As I told you, the germanium will sit here. Here will be the target. And around the target and the germanium will be the sodium iodide scintillators as an anti-compton veto. And the expected sensitivity that we plan to reach, well, let's put it in this way. Let's talk about the minimum daily reaction rate to reach 50% statistical uncertainty. Well, we can calculate this considering the detection efficiency, which is about 1%, the beam current, and I indicated here 200 particle microamps, which is a bit optimistic, but it's not impossible, as we already observed in the acceptance tests of the accelerator, and the data taking time of approximately 60 days. Obviously, these numbers are not the final numbers, but the order of magnitude is there so that we can estimate our sensitivities and how many reactions we could expect to observe. So for what concerns the P channel, so I'm talking about the 440 keV transition, we can expect up to 11 reactions per day. And this means that we can be able to measure this reaction in different scenarios. So consider the cross-section measured by Tumino et al. This is an indirect measurement. And in this case, if they are right, we can measure the cross-section down to approximately 1.6 MeV. And if they are wrong, and Mukamedzanov from 2019 is instead right, we can only measure this cross-section down to approximately 1.85 megaelectron volts. And if we consider instead the alpha channel, so I'm talking about this transition here, we can expect 3 reactions per day, approximately. So in the hypothesis that Tumino is right, we can measure down to 1.5 MeV. And in the opposite hypothesis, if Mukamedzanov is right, we can measure down to 1.75 megaelectron volts. So this is all for this, because we are still mounting the setup and commissioning it, and we're just preparing for this reaction to be measured. So let me come to my conclusions. And well, I just want to say that Luna has pioneered underground studies in nuclear astrophysics for over 3 decades now. And this Luna underground accelerator that we have allowed direct measurements at the lowest possible energies for very different processes, including hydrogen burning, but also Big Bang nucleosynthesis and S-process studies. And this is not over, because we intend to perform soon other studies at the Luna Megavolt Accelerator, which is part of this wonderful Bellotti facility that the LNGS has now put in place. And we will study reactions included in the S process, but also hydrogen burning, as I showed you, helium burning, and carbon burning. And this is just the start. And that's all from my side.